9.3, power series, Taylor-Maclaurin series. All right, so what we're going to look at now is very similar to what we did in 9.1. We had infinite series, but those series were just functions of n. They only had one variable in it. What's different in this section is now we're going to generate a series still by looking at a power of n. So n is going to be the variable in the series that generates the terms, but each term then is also going to have an x in it, okay? And so any series that has an x in it, we call in general a power series. It's a generic term for an infinite series that has something generated by either n. We could also have an I down here or a j or a k. We call that the index. But everything also has a variable in it. So when you expand the series by using, whole number values of n, you end up with a function of x on the right side. And it could be a polynomial. That's what we just studied in the previous section. But they could be something else as well, depending on what the rule of sequence has. All right, so an infinite series with an x in it is called a power series. And if we center it at 0, just like before, we can call it a Maclaurin series. If we choose to center it somewhere else, like at x equals c, we'll just call it a Taylor series centered at c. So that's all a Maclaurin series is, again, is it's a Taylor series centered at 0. And just like with polynomials, we can use these series to approximate functions. And sometimes they are super fantastic approximations for all real numbers, and sometimes they only approximate a function on a small set of x's, okay, not for all real numbers. So here we go. If we have a power series centered at c, exactly one of the following is true. Either the series, we say, converges at the center only, and let's talk about what that means first of all. When we talk about a power series converging or diverging, we're going to be interested in finding essentially the domain of the series, okay? And what that means then is, for what values of x does the series on the right-hand side, for what values of x does that then give us the values for the function on the left? And as I mentioned with sine of x, if we went out infinitely many terms, the graph of that polynomial will perfectly wrap itself around the graph of sine exactly if we used infinitely many terms. So in that case, we would say the domain is all real numbers. If you use infinitely many terms, then the values on the right-hand side in the polynomial and the values on the left-hand side for sine are exactly the same everywhere. But that's not always the case. We generated the polynomial, the Taylor polynomial for the natural log of x. Remember that? And we centered it at 1. And the reason we centered it at 1 is because we couldn't center it at 0. It's undefined. So if you represent the natural log of x with a polynomial, could the domain be all real numbers? No, there's no way a polynomial function can give us values of natural log of x for all real numbers, because the graph of the natural log of x doesn't even exist for all real numbers. So when we find the domain of a power series, we are finding the values of x for which the series that we're approximating with converges to the function which the series represents. Okay, so that's what it means to converge. It means that the series and the function value have the exact same values. Got it? We're using infinitely many terms. So now there's 3 possibilities. For any power series centered at c, exactly one of the following is true. The series can converge only at the center. Now what that means is that the series and then the terms that represent the function in the series are only the same at the center. And that's true for all series, just like it was true for all polynomials. It could be that the series converges for all x, which would be like the graph of sine of x. The series itself and the function it's representing are one and the same for all values of x if you use infinitely many terms. Or it could be that there exists a radius, we call it, that I could venture left and right, not for all real numbers, but a certain amount left and right, where the series is a perfect representation of the function. And then outside that interval, it diverges, we say. Okay, the series can probably go up to infinity, or maybe the function doesn't even exist. All right, so when we find where a series converges to a function, we're trying to find the domain of the series, essentially. For what values of x does the series represent the function exactly? not approximately. So we call R up above here the radius of convergence. All right, we call it the radius of convergence for the power series. If the series converges only at the center, guess what the radius is? How far are you allowed to go left and right of the center if it only converges at the center? 0. You can't go left and right at all. Okay, so we would say the radius on number 1 is 0. If the series converges everywhere, then we would say the radius is infinity. Feel free to go to the center and go as far left and as right as you want. If the radius then is some positive number, then we would want to find what that radius is. Okay? And so that's what a lot of this section is about, trying to find domains of power series, that is, trying to find the values of x where the series perfectly represents the function. Okay, and then once we find the radius, if it is a positive finite number, we're going to do kind of like what we did with the alternating series and the integral test. We're going to find then an interval where the values of x perfectly converge to the function. And that would be called the interval of convergence. And that does give us the domain. All right, example 1. Let's just jump right in and try it out. Because it's a lot of theory, a lot of words. You can learn a lot by doing. Based on the fact that a 4th degree Mach polynomial for e to the x is given by this. We knew that, right? They didn't have to give it to us. Find the nth term. That means find the rule of sequence. And then find the radius and interval of convergence for the power series. All right, so here's what they're saying. They're saying that e to the x is now equal to, not approximated by, 1 plus x squared over 2 factorial plus ... plus, and now I want to figure out what the rule of sequence is. Okay, how can I generate those terms as a function of n? Well, I think I can call it x to the n, right? Because they're increasing by 1. This is really x to the 0, x to the first, x to the second, x to the third. So maybe x to the n over. And then how is the denominator related to the exponent? N factorial. Good. And then plus ... This is one way to represent the power series. Okay? You could do it like that. You write a few terms, plus ... And just like in 9.1, you would then put the nth term. It's going to have an x in it, though, and then plus ... You could also then say this equals, and then you can kind of collapse it back down in sigma notation. Now, here's where you want to be a little bit more careful. It doesn't matter so much if you write the nth term like this, but whenever you can press it down to a sigma, you need to make sure that your starting value of n is going to give you a 1 when you plug it in. Because typically we could start at 0 or 1. So what does n need to be so that when I plug it in, I get a 1? A 0. Good. So in this case, we'd start at 0. Okay, so it's a little bit more of a burden when we're writing it in sigma notation. But those now are exactly the same. So here's what I want to know. And I guess we'll have to pick up here after lunch. For what values of x, then, if I used infinitely many terms in this polynomial, for what values of x will that polynomial be exact values for e to the x if I use infinitely many terms? For what values of x will the polynomial and e to the x be one in the same, identical? That's finding the domain of the power series. That's the same thing as finding the interval of convergence. I guess we can get started. Okay? Here's how we're going to do it. You're going to find the radius of convergence by the ratio test. Okay? And it's a very important test for this reason. Remember the ratio test said we're going to take the limit as n goes to infinity of the n plus first term divided by the nth term. And that's why it was important to have the rule of sequence there. So the n plus first term is going to be x to the n plus 1 divided by the quantity n plus 1 factorial. It's as easy as replacing both n's with n plus 1. And now instead of dividing by the nth term, we could do what? Simply multiply by the reciprocal of the nth term, which would be n factorial over x to the n. All right, so nth term times the reciprocal, the n plus first term, times the reciprocal of the nth term. And then it's just a matter of doing everything we did previously to get down to something that simplifies. Let's do the x to the n's first. I have one more factor of x in the numerator than denominator, right? In other words, when the bases are the same, you subtract exponents. N plus 1 minus n is just 1. So we're going to have an x to the first on the top. And which one's bigger, n or n plus 1? N plus 1. So if I write n plus 1 as n plus 1 times n factorial, then your n factorials divide out, right? And so that's it simplified. And n is going to infinity. I didn't write that. Now, because we're taking the limit as n goes to infinity, n is the variable of interest, and we're treating x like a constant at this point. Treat it like a constant. So what happens to x over n plus 1 as n plus 1 goes to infinity? Yeah, it goes to 0. This equals 0. Now, remember, the ratio test says that it'll converge when that number is what? Less than 1, right? Is 0 always less than 1? Yeah, so here's what we're saying. It doesn't matter what x is. It could be anything in the whole wide world. This is going to converge all the time, right? Regardless of what x is, this is always going to converge. So what does that mean? What do you think the radius is then? For what values of x does it converge? All values, yeah. So in this case, the radius of convergence is all real numbers. Or the radius, I'm sorry, is infinity. And the interval of convergence, which is also called the domain, is going to be all real numbers. The domain of this power series is all real numbers. So just like sine of x, as I mentioned, e to the x is a perfect representation for all real numbers by that polynomial with infinitely many terms. Okay? But the key is you have to use infinitely many terms. As soon as you use a finite number of terms, now you're back to a Taylor polynomial, and it only approximates it everywhere except the center. All right? That's pretty cool, because e to the x, remember, doesn't go up and down. It's just monotonic increasing. But apparently, if you used infinitely many terms, you'll have a polynomial that perfectly wraps around the graph of e to the x. Yeah. All right. Have a good lunch. We'll pick up there after lunch.